Thanks very much. And thanks for the invitation. I'm going to give an unusual talk for me in that I'm going to talk about stuff that is not quite fully baked yet, and some stuff that's not published yet, because I wanted to focus on a few things that I think get really overlooked every time we talk about bringing some aspect of robot learning or machine learning into HRI. So I think that when many of us think about, the challenges of bringing real machine learning into real robot domains, we think about the same sorts of things. We think about how you have to understand human social cues, and you have to deal with really sparse data sets and low frequency events and low frequency data. And you need to infer intent, and you need to deal with the vagaries of human feedback and how that's non-Markovian and non-stationary and all sorts of other good things. And all of that is true, and all of those are really good problems. But I want to maybe push away from them just a little bit today and think about a few other types of problems that show up when we think about bringing real learning into real robots. And I'm going to focus on three different things, and I'll motivate them by just looking at human environments. But just to spoil the punchline of all of them, I'm going to talk a little bit about tool use. I'm going to talk a little bit about trying to combine symbolic learning with statistical machine learning. And I'm going to talk about ways in which we can improve task and motion planning to deal with highly constrained environments, which most human environments are. So I'm going to go really fast, and I'm going to try to motivate things mostly based on the problem and give you a sense of what the solution is like. And I'm going to be really kind of hand wavy with exactly how technically they work, mostly because if you want to see the paper, ask me. I'm happy to send you a copy, even an advanced copy. But I want to get you sort of thinking about these different ideas sort of from a different point of view. Okay, so first topic. We humans build environments, and boy, do we love stuff. We have stuff all over the place, and an awful lot of that stuff are things that are designed to be used by our hands. And we completely litter most of our workspaces, spaces where we actually function, with more and more specialized tools. Now, how is a poor robot going to deal with this? How is a poor robot going to be able to get into a kitchen or a workshop or even a family room and deal with all of the range of tools that are suddenly going to be there? Not only that, we don't only use tools for their intended purpose, we use tools creatively. We all grab that one random stick and use it as a back scratcher, and we use that nice looking ladle there, not to actually be a ladle, but to lift the hot pot lid off of the boiling water. How are we going to have systems that deal with all of that? So recently, a couple of my students got interested in this problem, and I'll show you some quick results using a system they call TriStar. And the idea here is to be able to do three things: to be able to rapidly learn to use tools with just a very few human demonstrations, to then be able to generalize one learned tool to another similar set of tools, and then finally to be able to transfer those skills from one physical set of kinematics to a different set of physical kinematics, one robot to another. Okay. So what kinds of things am I talking about here? I'm talking about, well, lots of different kinds of tasks. We looked at 7 different tasks. We gave the robot 10 demonstrations of each. That is, we had a human perform 10 knocking tasks and stirring tasks and pushing tasks and scooping tasks. And then we just let the robot go from there. Now, some of this was basically a learning from demonstration problem, and part of it was a kinematic exploration problem. But we wanted to make it a little bit realistic. So rather than having, sort of a standardized grasp point for all of these tools, we ensured that every time the robot picked up the tool, it was picked up slightly differently, because that's what's going to happen in the real environment. We're never going to get that exact perfect grasp point. And again, without giving you all the details of how we do this, what we end up with is a system that's able, with very few examples, to be able to pick up on a task, take a robot arm, a standard, in this case, a UR arm, and regardless of how we pick up this extra piece of kinematic structure on the end of the robot's arm, we're able to adapt to that system and accomplish a stirring task or a knocking task or some sort of pushing task. And I won't go through and show all of this. I don't have time for the whole video, but just to give you a couple of quick samples, here's stirring, here's pushing. And again, we can't pre-program any of this because each time we pick up the tool, it's a slightly different kinematic structure. Okay. Second, we want to be able to take those learned skills and without any retraining, without giving it any other additional demonstrations, be able to generalize from an initial tool to something similar. Now, we do a little bit of fancy machine vision to do this. We have to do things with point clouds because we have to try to map and morph one tool onto another. So if we start out knocking with a gavel and then we want to use a rolling pin to be able to knock on something, then we have to be able to identify similar structures in that physical object. But in fact, again, with just a really simple underlying model, we're able to take one trained system and generalize it to a number of different substitute objects without any retraining. Okay, here's one more example. Here's some stirring task. We initially train with a spatula and a nice big wooden bowl, and we do with everything from a spoon to a fork to a wooden mallet, and with various sized target objects, target bowls. And one more example here. Here we've got something that we're going to use to push, starting with something that's more like a garden rake and using a variety of different things, including sometimes pushing from the side, like that lower lower left hand object. Finally, when we deal with tools like this, we want to be able to generalize that to different systems. So here we took 3 common commercial arms, one from UR, one from KUKA, one Baxter. And we picked one of the objects, one of the pairings that we had that we knew all of the robots could pick up. The Baxter's not as strong as the other arms, so we kept the things that were lightweight. And the KUKA is not as long, doesn't have as much reach as the others, so we kept things that were relatively short. And again, with no retraining, or rather having just trained this on the UR, we're able to get one of these other systems that has a different kinematics, different dynamics, to immediately pick up and using this underlying model, be able to use a variety of tools to accomplish a task. This is what we need for human environments. Not because there's a human right here in the loop, but because this is what human environments are like. All right, second thing I want to point out. When we talk about working in human environments, and especially when we talk about working around people, human environments have rules. There are things you're allowed to do and things you're not allowed to do. And for a robot, those rules are going to change pretty frequently. It might be okay to start a fire at some point, and it might be okay not to start a fire at some point in this picture. It might be okay for the robot to come along and put the remote control away, but not when I'm sitting there watching TV. How do we integrate that into most machine learning type structures? Most of our machine learning is a low-level statistical process, usually over some graph structure, some MDP, SMDP. How do we get to the point where we can enforce this high-level symbolic structure, sometimes given to us by language, sometimes given to us by context? But how do we enforce that structure on this low-level statistical process? So one thing we've been working on is exactly that. So imagine you have your favorite reinforcement learning or low-level statistical learning. It could be anything from, let's say, Q-learning to deep reinforcement learning to even just standard deep learning. Somewhere underneath there, you've got a graphical model that talks about states of the worlds and transitions. And so we're going to just abstract that away and just talk about this as a graph. put whatever constraints you'd like on this, whether it's just a finite state automata or a POM-DP or whatever you'd like, but it's a graph at some level. The idea here is that we're going to take this graph and we're going to treat it as the underlying data structure, but a data structure that we have to look through a very particular lens in order to see it. Now, those of you who have been around like me since, well, the mid-90s, remember the point where we didn't have PowerPoint and we didn't have Keynote. We had good old overhead transparencies. And you would have a nice actual piece of plastic that you had printed or written information on, and you would lay that down on top of the projector. And in the same way, we're going to take each of the rules that we would like to enforce here, and we're going to lay it down on top as a transparent overlay. So if I want to tell this robot who's working in my kitchen, never touch the stove, I'm going to have one overlay, one rule basically, that's represented as a way in which I can view this underlying statistical model that effectively blocks certain transitions and allows others to be seen. That is, when I look through this overlay, I'm going to be able to see some of those transitions, and others are going to become opaque. Now, why do I do that? Well, what I'm effectively doing is I'm blocking out any of the transitions that would say, let's go touch the stove, any of the things that are going to break the rule that I have now come to enforce. Now, why do I want to think about it as an overlay? Well, one good thing here is that I'm not changing the underlying statistical model at all. That can keep running, can keep learning, can keep changing, and it won't affect or influence the rule. That is, I can't break the rule by continuing to learn. In the same way, if I want to add a second rule, like let's say right now, don't move the remote or don't move my coffee cup, I can picture that as just another transparency that I'll lay down on top of this pile. When I do that, now I have to view any of the transitions through both of these overlays, both of these filters effectively, and only the ones that pass both of those rules will I be able to see and will I be able to utilize. But again, the underlying machine learning system will just keep running, the underlying statistical system. Now, what's good about this? Well, one thing is that I can then decide to break some of the rules that I've enforced. Let's say now I learned to trust this robot a little more and I actually wanted to go make some tea for me. Okay, so maybe I want to get rid of that rule about touching the stove. Okay, so we can revoke that. And now suddenly, because we've kept this underlying system the same, we're able to keep moving and keep going without actually losing any data, without losing any experience. We've done this with,
bring me pieces from the
sorry,
left
I'll
side.
mute Jake here for a second. But we've done this with real systems where in this case, we were doing some collaborative manufacturing. We were trying to build chairs and Jake was giving the robot rules about using things on its left or its right or using things of a certain color. And based on that, we're able to limit what kinds of actions the robot can select, enforce those rules for some amount of time, and then revoke them. When we do this in human situations, we find that we actually produce far fewer errors than we did with either pure statistical modeling or pure symbolic modeling. And we do that because people are much happier and easier to and find the system easier to use because it captures their intuition about how this should work. Okay. Again, I know I've given you none of the details about how this actually works, but hopefully the intuition is enough to get you thinking and get you excited about something. All right. Last little bit that I'll put for today. Human environments are cluttered. Those of you with kids have no doubt about this. Those of you who don't have kids and have roommates also have no doubt about this. One of the things that makes it really difficult to operate in those cluttered environments is that most of our planning systems don't do a good job of dealing with complex environments. They're designed for complex kinematics, but not for complex world conditions. That is, when we think about task and motion planning, we think about a robot trying to do something, and we create a list of options that basically we have to search through. And if the robot is trying to move something around, we have got a goal, a particular action, this push action that we want to happen. And we might have multiple different possible routes in which we could accomplish it, pushing it one way or the other. But for environments that are highly cluttered, environments where many things might not be possible, they're infeasible, or where they might be highly constrained in how they can be done, this task and motion planning process is extremely inefficient. That is, we search through hundreds of thousands of possibilities to find a very few that are actually viable. Wouldn't it be nicer if we could take that environment complexity into account somewhere? That is, effectively in an infeasible task, be able to say, look, no matter which way you push this thing, you can't get it out. Or effectively to say, look, this really narrow constrained object, you can only use it in a few certain ways. Effectively limit the search tree, not just based on the complexity of the robot kinematics, but also based off of the world structure. So the variant that we'll propose here is to say, to take our typical task and motion planning pipeline just as it is, and we'll insert a step into the middle. In between task planning and motion planning, we'll introduce something that we'll call affordance planning. That is, do the environment objects that we're dealing with afford a possible solution? And if so, let's forget about anything else, because these are the only things that can happen in these constrained environments. Okay, again, I've given you the flavor of the solution, but let me show you it actually working in a bunch of examples, both with a real robot and in simulation. Here, the goal is to take the green, that is the object on toward the right, place it in the blue box, and then place it on the stove, the red box with the swirly top. And in fact, even for relatively complex tasks where I have to move one tool to manipulate a second tool to get the object that I need and then manipulate it, when we start doing this with this affordance-based planning, we can often do things that aren't totally possible with traditional task and motion planning, because we can do them in a competitive time frame. Thought I wasn't going to show you the results, but I will just quickly. In many cases, we can take things that time out after 10 minutes of searching and find solutions in under 30 seconds. And that's using the same traditional planners. Now, sometimes it comes at a cost, and if there's a really unconstrained environment, we might take, what was a 2-second planning task and turn it into a 4-second planning task. But the fact is, most of our human environments are not those unconstrained worlds. They're the constrained and they're the infeasible ones. All right, I got to stop there. But just to remind you, there are these other great problems out there. Let's study those basic ones, but let's also get to some of these really interesting ones. And let's look practically at the kinds of environments and the kinds of operation that we expect these robots to do. All right, thanks everybody.